Okay, continuing our discussion in probability and how the integral can help us work with this is the phenomenon of wait times and equipment failure. So what's really interesting is that if you're trying to figure out the time you wait in a bank or a restaurant or something like that, what's the likelihood of waiting a certain amount of time, or what's the likelihood of some equipment kind of failing within the first couple hours or years of use, what's interesting is that it turns out that this probability density function, which is dependent on mu, our mean, happens to model a lot of these random phenomena. So this probability density function looks like nothing if t is less than 0, because we're talking about time, so we're not interested in things failing or waiting before they exist. And then this guy here, the inverse of mu, 1 over mu, e to the negative t over mu, when time is greater than 0. And this creates an exponentially decreasing function. You can show that this is a convergent integral. We know this area is going to be 1. But what's really interesting about it is that if you look at it, if you're going to wait, you're going to wait a lot, or you're going to fail a lot at the beginning, and then you're going to have less likelihood later on of that occurring. I actually used this model to try and get my HVAC company to replace my new air conditioning unit, because it failed numerous times right in the beginning. And so I said, once a lemon, always a lemon. I'm going to use some math to kind of explain that to you. Needless to say, they did not give me a new HVAC unit. But I will continue to use that idea when we're talking about the probability density function. It's really likely to occur if it's going to occur at the beginning. So in our example, we're talking about a restaurant. And again, follow along with your handout to get the full problem and the full kind of description of these things, and so that you can understand the whole problem that's going on. So for our problem, we're going to a restaurant, let me see, and no, I'm lying, it's a bank. We're going to a bank, and this bank has an average waiting time, or a mean waiting time, of 8 minutes. And in the first part of the problem, we want to figure out the probability that a customer is served within the first 3 minutes that they get there. So if the average time is 8 minutes, we should expect a kind of low probability that they're going to get served very quickly in 3 minutes, but likely that somebody will. So the probability that someone gets served within the first 3 minutes is the integral from 0 to 3 of f of x dx. Now, of course, remember, nothing's happening when time is negative, because we're not interested in somehow turning back the hands of time here. So plugging into this part of my formula, I have 1 over mu, or 1 over 8, e to the negative t over mu, negative t over 8 dt. And as it turns out, this is a pretty easy u sub. And so if I take this antiderivative, I end up with just negative e to the negative t over 8, evaluated from 0 to 3. And plugging all of that in, I'll get negative 1 over e to the 3/8 plus 1 over e to the 0, or 1 minus 1 over e to the 3/8. Now that's our exact answer, and of course that's not really interesting. It doesn't give us a very good idea. So in this case, a decimal approximation might be useful, and if we get the decimal approximation, there's a 31% chance that if you go to this particular bank, you'll be served within the first the first 3 minutes. You'll probably get served, on average in 8 minutes. So let's continue with this problem. And the next part of the problem asks us, what's the probability that someone waits more than 10 minutes? And again, we might expect that probability to be small because the average wait time is 8 minutes. So let's talk about that. We're looking for the probability that someone waits more than 10 minutes. So that's going to be from 10 to infinity. Of course, we hope that you're not waiting at a bank into infinity. But same function, 1 over 8, e to the negative t over 8 dt. Now we're going to have to use some processes here because we have an infinite bound. So we'll go ahead and manage that, but I don't think it'll be too bad. And we'll end up with, and I'm going to use a different variable than t because t is my variable of integration. So maybe I'll use b for bank. As b goes to infinity, 10 to b, 1 over 8, e to the negative t over 8 dt. All right, so this integral is not too difficult to compute. Again, it's a simple u sub, so we end up with negative e to the negative t over 8, evaluated from 10 to b, which will give me negative 1 over e to the b over 8 plus 1 over e to the 10 over 8, whatever that happens to be. And something nice happens with the first part of this limit. So here we have infinity divided by 8, which is of course just infinity. And so we know that as we take the limit as b approaches infinity, this first term in my limit should travel off and actually give me no value whatsoever. And so there's no b, so this limit is independent. This constant is independent of the limit. And I get that the likelihood that someone has to wait more than 10 minutes is 1 over e to the 10 over 8. Now once again, that's not very descriptive about what we want here. So instead, if we get the decimal approximation for that, it's 0.29, or about 29% chance you're going to wait. Now, if you put the integral from negative infinity to infinity of this function into Wolfram alpha, which you can do, you'll see again about these percentages coming out in such a way, the probability you can kind of visualize in terms of area of the probability density function. It's kind of cool to look at that. All right, so the last part of this problem asks us to play around with the median. Now, the median waiting time might be the same as the mean. It might not be, but we can calculate the median waiting time for this particular bank if we just plug into that formula that we had for median. So the median is the x value m, such that when we cut off the probability density function at that value m, we get half, 1/2, since the total area is 1. So we're looking for this guy, we're looking for m, which means we're going to have to go through kind of the integration process in a different way, and then wait and figure out if we can work backwards for m. So the function that we were working with was 1 over 8 e to the negative t over 8 dt, and we'd like that to be 1/2. So again, I'm going to have to set this up as a limit. B sounds nice for bank, and we're going to be going from m to b of 1/8 e to the negative t over 8 dt, and we'd like that to be 1/2. So we've done this integration a couple times now. And we know it's negative e to the negative t over 8, evaluated from m to b. And again, we want that to be equal to 1/2. So I think we know what's going to happen with this b part. And we know that, this is actually in the denominator, or if I plug in infinity here, e to the negative infinity is 0, or 1 over e to the infinity is 0. And so this part of my limit ends up giving me nothing. This part is independent of b, so it's a constant, and so I end up with the value of this limit being just e to the negative m over 8 equals 1/2. Now remember the goal here, right? The goal is to figure out what this x value is, or this m value, so that we cut the area under the curve exactly in 1/2. So I'll take the natural log of both sides. And I'll get negative m over 8 equals the natural log of 1/2. And then if I multiply by a reciprocal, I'll get m equals negative 8, natural log of 1/2. Now again, that's our exact value. We love exact values, but in this particular case, that doesn't help us necessarily visualize what's going on the graph. So it turns out that our median occurs approximately at 5.55 minutes. And so in this case, our mean and our median were different, but it was still an interesting idea to say that the median waiting time is 5.55 minutes, whereas the average waiting time was 8 minutes. So this problem was interesting. Again, if we know the mean value, we can find out a lot about information about those probability density functions as well.